So he was asking about the commutation of the two vectors. You do it with the elements of the vector, and you have the multiplication of the elements of the two vectors minus the the elements of the vectors flipped. Okay. Good. So let's continue with curvature. Which is something similar to tensor, but actually to torsion, sorry. But now it's not related to the commutation of single covariant derivatives, but is related to the commutation of double covariant derivatives. Okay? For our curvature that we label with R is swallowing a vector field, another vector field, and another vector field, and is giving us a vector field. And now this is defined as R. We take again two directions, V and U, two vectors identifying two directions, and now it's applied to another vector. And this object, R, is defined as the covariant derivatives with respect to the first vector. So that's the directional derivative with respect to the vector V, multiplied to the covariant derivative of the second vector, which is U, applied to S. Minus the same stuff, but first with respect to the U vector, then with respect to the V vector, applied to S. And then we need to check as well the fact that the covariant derivative is applied to the commutation of the vectors, because perhaps the elements to which it's applied, they are not commuting, and therefore this must be V and U, again applied to S. So this is the curvature. As the torsion, you see that it's antisymmetric with respect to V and U, because if we flip V and U, we get exactly the same stuff, but this guy is going to be in front. Therefore, we have a minus. Okay? And same goes for the other end. So you see immediately from its construction that it's symmetric with respect to V and U. Now, the meaning of this object, we follow the same way of reasoning that we had before, meaning we have a vector V, so we start from a position A, we have our vector V, then we have our vector U, which is pointing, I don't know, perhaps here, like that, and then we have another vector S. Where is yellow? Here. Which is pointing, I don't know, in this direction. Then we apply the parallel transport. We parallel transport in the direction of V, and we get something. If there is curvature, as we've seen with the exercise on a sphere, it might have a different, is a vector pointing in a different direction. So this would be parallel transporting along the V direction of S. Then what we do, we parallel transport it along the U direction, and we might get something even different, which is, I don't know, perhaps like that. So we parallel transport along the U direction, therefore is U applied to this guy, which is V and S. I do exactly the same for the other vector, so for S, but I go the other way. So I go from here and I go there. Okay? So I have the first derivative, the covariant derivative, directional covariant derivative, which is applied this time to V, and then is applied to U. Therefore, I'm going to get something different, as we have seen, because the covariant derivatives also are not commuting, I might get the vector S. So I get this guy coming from this direction, and this guy, which is the V, the U, S, coming from the other direction. This is from direction 1, direction 2, and this is the 1, and this is the 2. Okay? And curvature is exactly this difference. This guy minus the other guy. That's the meaning of it. So it tells you about the non-commutativity of double derivatives when applied to a vector. Good. As before, we need a tensor. And we want to identify once more what are the components of the tensor. And once more, we are going to use a Cartesian frame. We are going to use a set of bases describing a Cartesian frame. Now you see that there are more vectors applied, so you understand that there are more indices with respect to before, I, J, K, and L. And I let the space here because that's associated to E. Okay, so take care about the order of the indices. And as before, we just apply the definition of our tensor. So we are applying it to, should be, yes, a one form, because we then, no, that's correct. Because then for the tensor, we need to apply it to one form. So it's exactly the same thing that we had before. 1, 2, and 3. And we get a real number, right? So we have the basis for our one form. So we have the XE. And then we have our object that it can be represented this way. So we have RS. We have the basis, the E. Then we have the basis, the J. And then we have the vector, again, which is another the J, this K, I, wait, sorry, I, J, K, and L. K and J, K, L, and J. Okay. So the way of ordering is purely conventional. Okay? So take care, because in different books, in different texts, you can find the orders flipped. Okay? It's purely conventional. And there was not an agreement in the end to decide for one convention and get everybody on the same page. So take care of this. Okay? So let's write it down. Order of indexes is conventional. Okay, good. That's our object. As exactly as we did before, we are going to basically use the explicit expression for the curvature that is given up here. As before, this guy is going to commute. So this is V and U are commuting. For this object is equal to 0. And the 0, the covariant derivative with respect to the 0 vector, is equal to 0 vector component E, the E, which is 0. Okay? So when we apply the procedure, this guy is going to disappear. We are not going to see it. In the end, I don't repeat, I don't go through all steps because it's exactly analogous to what we did before. We get the components of our curvature, which is K, I, L, J, minus the L, I, K, j plus e k l gamma l j minus e l gamma affine connection l k j. Let me see if they are all clear, the symbols. Yes. This is our curvature tensor. These are the elements of the curvature tensors. And you see that we keep trace of the fact that this object deals with non-local quantities because we can see that it's associated to derivatives of the affine connection. And if you're choosing a frame in which we can make the affine connection vanish, meaning all of these would disappear, the derivatives would be different than 0. Okay? So you cannot make it vanish in presence of curvature, in presence of a curved space-time. Yeah? That's KLJE, KJ, gamma, that's a dummy, gamma, 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 gamma. Okay, that's correct. So this guy was a dummy indices, and it was applied to the other affine connection, okay? So the indices are I, K, L, J. These are two dummies. Okay, so you see you cannot make it vanish in presence of curvature. Therefore, the condition affine connection equal to 0 doesn't tell you about the curvature of space-time. Whereas, and you cannot use it as a condition to say, there is or there is not a gravitational field. But the tension, if you have R, I, J, K, L equal to 0, then you have a curved space-time. Then you have gravity. Space-time is curved. And the way around, if this is different than 0, then you have gravity. Okay? If Rij is equal to 0, then you mean that you are dealing with a flat space-time. Okay? Again, on the lecture notes, you find the steps from here to here, one by one. I didn't miss a single individual step, no matter how trivial it was. Okay, so you find everything. And in any case, it's exactly the same procedure that I showed you when we derived the torsion. So I didn't really miss anything here. Good. Now, we can also see at curvature in a slightly different way. I want to give it to you such that you have another perspective. But this time we are not going through two different paths to arrive in the same position. And if you wish, together is a closed loop, okay, in two different directions. But it's kind of associated to a closed loop. Now we take a closed loop for real. So we take one vector, we start from here, and we go to another location, let's say, whatever. We make something like that, okay? Then what you have is that you are parallelly transporting your vector. I gave it a name, no? So let's take a vector v. We just parallelly transport it around. You see, we're going, should be straight. You go around and around and around, and at the end, we arrive with something like that. Okay, through parallel transport. And again, you can see that there is a difference, and that's associated to curvature. So also performing such a path would allow us to identify the curvature. Now, the nice thing of this procedure is that we can exploit the Stokes theorem that allows us to compute the integral along, so we can transform the integral along a path into an integral over an area. So we have an integral over a path, so a length, and we can have it as an integral over an area. Okay, that's what the Stokes theorem allows us to do. Plus, it's going to give us a different equation that contains curvature, but now you see curvature not as associated to covariant derivatives, as we did here. It will kind of pop up, because here we started with a definition, right? And then we quantify the object. What I'm going to do here, I will skip a few computations, but what we are going to do in this way is that curvature pops up. Okay? And again, is associated to path, and it gives you the difference between the same vector but going through different directions, in this case, through a closed loop. So, one, we basically apply parallel transport. Of a vector u along some direction. So we are making infinitesimal steps. We are parallel transporting the vector u along an infinitesimal direction, and I'm taking the basis as a vector. And we set it equal to 0. That's the parallel transport, right? Along a direction given by the basis alpha. Then we can use the explicit expression, the alpha u nu, because by construction, this guy is the alpha, because is the covariance derivative with respect to a basis, so is the alpha. Okay, so that's the meaning of it. Then we have is a vector, so we have plus the index nu, then we have the derivative alpha, dummy index gamma, and we have u gamma equal to 0. Now we can get this guy here, the alpha u nu equal to minus the nu alpha gamma u gamma. Now you can see that the affine connection is telling us how this guy is changing when we make an infinitesimal step. And with this guy, we go all around the path. For 2, the change after an infinitesimal shift the x alpha is the u nu, so is the change in our vector, equal to the derivative of our vector, which is related to the affine connections, times the shift, the x alpha. And now we can plug this guy into here. Therefore, this is equal to minus nu alpha gamma u gamma. So we can see how our vector is changing infinitesimally after a small step. And you see that this is kind of associated to what we did before, because before what we did was we looked what is the change after a closed loop, but we had two shifts, and it gave us the change, the total change. Here we are looking for the infinitesimal change after a small shift of the same quantity, which is the vector that we are shifting around, that we are parallelly transporting around. Now, what I said, we have our closed loop. We want to know what is the total change in our vector. Therefore, we just perform an integration. 3. Total change is just the integral along the path. The u nu, so the total change in our vector, is going to be to the integral along a closed loop of the u ni, which is the guy that we wrote up there. So that's equal to minus integral. Then we have the affine connection. Nu was the alpha, yes, alpha, gamma, u, gamma. And then we have the x alpha. Now, for convenience, one can define this object. You see we have a dummy index. Therefore, we have 2 free indices, which is nu and alpha. And I can call it b, nu, and alpha. So you see, it's a tensor of rank 2. It's a type 1, 1. So that we basically have equal to minus integral phi b nu alpha the x alpha. And now we use Stokes theorem. And now we can transform this integral along a path into the integral over an area. So we have the derivative of b nu alpha over the x, actually another index, beta, and the area, the S alpha beta. See, this is a slice alpha beta that identifies this area. Okay, so what I did here, I applied Stokes theorem. And guess what we do now? Well, we have B, which is defined up here. We applied into here, and then we just compute the derivatives of this object. It's a tensor, so remember that we have 2 indices. Therefore, this is going to give us 2 affine combinations. So it's a linear combination through 2 affine connections that pops up, 1 per index. Okay, 1 with a plus and 1 with a minus. I spare you the steps. That anyway, again, you find step by step here. And in the end, you get minus 1/2 the integral. And then guess what? We get the nu alpha gamma comma beta minus nu alpha sigma sigma beta gamma minus nu beta gamma comma alpha plus nu beta sigma nu sigma alpha gamma u gamma ds, and then should be alpha beta alpha beta. And look at this guy. This is the curvature tensor. Okay, you see, it pops up. It pops up and has the meaning that I gave you before. And look at this equation, which is very nice, because this is the total change. This guy from here to the end there is equal to du nu. For du nu is equal to minus 1/2 R nu alpha gamma beta U gamma ds alpha beta. Now, over the tau ds, no, that's it. Okay, good, du. Okay. Now, look at this guy. If we now compute an acceleration out of it, and we take u to be the forward velocity associated to a particle going along a geodesic, this is actually an acceleration. This is dx nu over the tau squared. An acceleration. What is gravity doing to particles? It looks like a force, as we have seen. You have an acceleration. You see the connection between gravity. And you see that the acceleration is proportional, is related to the curvature. Therefore, you see how this guy is related to the physics we are dealing with. Therefore, this is one of the guys that we would like to have in the final field equations. And you see how this is associated to accelerations. We will see it better. Okay? Now I just wanted to show you how the curvature popped up. Okay? So if you want, this is some extra that I'm giving you. Definition I gave you at the beginning was already sufficient. And we're going to see how this thing here is associated, is related, actually is the geodesic deviation. Geodesic deviation equation. We have the geodesic equation, and then we have the geodesic deviation equation. And if I say it like this, is not super clear what it means, but we are going to see it better and in a more clear way when I'm going to assume torsion free, and we are going to have the actual acceleration of particles. Okay? Or if you wish, better, the acceleration of a particle with respect to another geodesic which is nearby. Okay? Which is exactly the game that we wanted to play before. Because we had the mass, we had the particle, we had a particle, we had one acceleration, another acceleration, and what we are investigating here is the difference between these two guys, the difference between two different geodesics that tells you about the presence of gravity. Okay? So we are going back to it. Now it's nice to see that the curvature tensor just pops up by making a loop along a closed circle. Now, back to the commutation of the covariant derivatives. And I'm going to show you, that's something that is quite often missed, the fact that if we have our curvature and we have our torsion that for the moment we are still letting survive, so jk, we are going to see how these two guys are related to the commutation of derivatives, of covariant derivatives. Okay, so let's start the business. So their relation with the commutation of covariant derivatives. So that's again quite a painful computation. I give you the main steps, and then all the individual single points, you will find them in the lecture notes. Well, what we are going to do is exactly that. So we are going to evaluate the commutation of covariant derivatives once it is applied to a vector. We use the definition of the commutator, which is the alpha T beta V nu minus the same thing, but with indices flipped, the alpha V nu. Then we give a look at this object first, which is what? It's a tensor. Two indices, one up and one down, is a tensor 1, 1 of type 1, 1. Therefore, the alpha applied to a tensor, so I'm applying the alpha to, now let me write it like this, with the comma. So you see that I'm applying the alpha to a tensor of type 1, 1. This makes it a little bit more apparent. That's equal to the standard derivative with respect to alpha of our tensor, nu dot comma beta, yes, plus the affine connection related to the upper index because there is a plus. Therefore, we have gamma with respect to alpha, dummy index that I used gamma. And again, V gamma, comma, beta, minus, now is the affine connection that is associated to the other component beta. Therefore, again, with respect to alpha, now beta is down, alpha is up, and then we have V nu dot comma and gamma. That's what we have here, minus the very same stuff, but alpha with alpha and beta flipped. I'm not going to copy it. Then what we have? We have these covariant derivatives. You see? They need to be exploded. So what we have, I copy from here because there is too far. So we have the alpha, which is this guy, times the covariant derivative of the vector nu with respect to beta. That gives us V beta nu plus affine connection nu beta gamma V gamma, plus the rest. I'm not going to touch it, otherwise it gets too long. Beta minus gamma alpha beta, yes, V nu gamma, minus the same stuff but for this term, which is identical, but with alpha and beta flipped. Okay? Now, we can explode these terms too. These get quite a long expression, but you know how to express a covariant derivative. So you see that are going to pop up terms that are multiplied. You have an affine connection times an affine connection which is contained here. And there are terms that are associated to these affine connections times the derivative of the vector, right? Because the covariant derivatives, as we see up here, contains a standard derivative. Okay? In the end, there are terms that cancel out. You're going to have terms that contains the affine connection, and you end up with an expression that looks like this. You can again re-identify the curvature applied to a vector. That's no surprise. We started with a commutator of covariant derivatives, and we have seen how the commutator of the covariant derivatives is associated to the vector, or to the curvature tensor, right? I mean, you will see this is just a stupid combination of things and reshuffling of terms. Okay? No physics involved. Minus something that, as I mentioned, because we have this covariant derivative that contains the standard derivative of the vector, something that is related to the standard derivative, so the covariant derivative of vectors, the gamma, and this guy is actually the torsion. That's something that is often missed. So if you're looking at the total commutation of covariant derivatives, there is one associated to the curvature and one that is associated to torsion. This is usually missed because if you think a torsion free, you just say, this is the only connection we have. Okay? But that's not the case. So you see that the commutation has two components, one which is associated to vectors, and one which is associated to covariant derivatives of the vector. In the definition before of the curvature, this guy didn't pop up because we were not sensitive to derivatives of vectors. Okay? Okay, this I already mentioned. Good. Now what we have? We have this expression for our curvature. We understood what our curvature is. So we see that we can define it. Here is the construction of the tensor defined as the commutation that involves double derivatives. And we end up with this expression that involves the affine connection. This is generic for any affine connection. Then we also gave a look at what happens when we do a closed loop of a vector. We have a vector, we go around, and we go back to the same place. Like we are here, I have my vector pointing north. I'm going to the North Pole, and then I come back here. I will obtain a vector that is pointing in a different direction. And again, you understand that this is revealing with respect to the nature of the curvature of the manifold in which we are living. So again, as I said, we are parallelly transporting our vector. We are going in infinitesimal steps. So I make the parallel transform with respect to a basis direction. Okay, and then I can do the same with all the other directions. And by construction, this is the covariant derivative, the directional derivative with respect to the basis. It's written in this way. Right? This is the derivative with respect to the alpha direction by construction. This allows us to identify the derivative of our vector with the affine connection, with a term related to the affine connection, which allows us to see what is the change of a vector whenever we shift it, we parallelly transport it by an infinitesimal step in one direction. That is this guy. Then what we do our trip, we do our field trip, we go all around the Earth or whatever, or the space-time, and we come back. And we compute the total change in our vector, which is nothing but an integral along the closed path of the u that we define up there. This contains our affine connection, that you see there is a dummy index, two free indices up and down, and this is a tensor of type 1, 1. Now I can apply Stokes Theorem, where we can compute from an integral of a closed loop, so that's the path integral or a closed loop. We can transform it into an integral over an area. And just by making explicit computation for these derivatives, we arrive to identify the curvature. So it pops up. Okay? So you see it's an object that exists somehow. It is strictly associated to the space-time nature and properties. And then if we get just this little bit, we can identify this object, and you see that there is an association between the acceleration when we are going along a geodesic with respect to the nearby geodesic, which is proportional to the curvature R. That's what we were looking for. We were looking for this sort of signature. for difference in accelerations between running along two different geodesics. Okay? And here I'm making free-falling objects, but it can be also for circular objects, for circular orbits. Take this orbit. Take this orbit. Here, the acceleration, the velocity, the tangential velocity is way larger with respect to this one. Right? Mercury orbit. I mean, now I don't remember how was it. How long was the year of the orbital period of Mercury, but it's way shorter with respect to the one of Earth. So this guy will move forward in the same amount of time. We will find something like that, and the little Earth moved by a bit. There is a difference in acceleration, you see? So it's not just free falling means also closed orbit and means a lot of stuff. Closed open orbits or whatever. Okay? Good. So yes, we have a very powerful instrument to investigate the space-time and to identify the curvature and therefore gravity. Then we made a step backward, and just to allow you not to miss something, we investigated once more the commutation between covariant derivatives. And once we apply the commutator of covariant derivatives, we see that there is this object popping up with these double covariant derivatives that we can just explode by just using their definition, just how they are constructed. And in the end, we get a combination of affine connections. Then once you recombine them together, you can identify the curvature applied to a vector and torsion applied to the covariant derivative of a vector. So the full commutator actually contains the two together. And the two together gives you the full picture. Okay? In GR, as I said, this guy is going to disappear. So from now on, that's the last time we see. I will mention it again, because if there are deviations with respect to standard GR, I will say, look, if there is torsion, it will be different. But we are never going to use it again. Okay? So this is the end of torsion. Okay? So torsion is going to be equal to 0, and we are imposing it. So from now on, we are speaking about general relativity only. Up to this moment, we were more general, and the concepts that you learn about differential geometry could be applied also to theory that are not GR. Okay? There are the Einstein-Cartan theories that uses torsion different than 0. There are other theories as well that uses torsion different than 0. So now it's gone. And once we do that, we will also apply our other constraints on the derivative of the metric. And to have an explicit expression of, so the two together, to have an explicit expression for the affine connection, which is given by the Christoffel symbols. Now everything is explicit, everything is associated to the metric, because we have an explicit expression for the affine connection with the metric. And now you understand that the curvature is a function of the metric. And the metric will become our field. Will become, once we compute the Einstein's fields equation, it will become the field that we want to constrain. We will have the association between the geometrical part that contains the metric through various combinations of the curvature tensor to matter. And this will be gravity, okay, as seen in GR. Good. We can stop here. And next time we will continue and we will make the curvature explicit with respect to the affine connection assumptions, torsion-free assumptions, to have our explicit expression of the curvature with respect to the metric. We will identify in very few steps the Einstein's field equations. So next week we should be able to see the Einstein's field equation, probably already on Monday. Good. See you next time.